So in this video, I wanted to talk about how we can derive the area of a circle. Remember, the area is pi r squared for a circle. So I wanted to talk about how we can derive that using integration. Okay, so if we have a coordinate system like this, and we have a circle in our coordinate system that looks something like that, and it doesn't really look like it, but just imagine it's centered at the origin, even though it's not the most beautiful thing in the world. We center at the origin, and it has a radius r like that. Then we can say, alright, here we have the coordinate x equals r. Remember, this is centered at the origin, so x equals 0. And then here we have x equals negative r. Okay, so if I were to integrate the formula for the circle, and I would integrate it from x equals negative r to x equals positive r, that would get me this area here, right? Then I can double that integral, and that'll give me the area of this bottom segment here. So that'll give me the area of the total circle. So what I'm saying is, if we take the equation of a circle, integrate it across the top half, and then double it, that'll give me the total integral for the area of a circle. So let's look at the equation of a circle now. If a circle is centered at the origin, and we're all going to do that just to keep everything simple, we will have x squared plus y squared equals r squared, and then solving this for y, I will get y is equal to plus or minus square root of r squared minus x squared. Okay, now since I said we're just going to be dealing with the top segment of the circle, we can just ignore the plus or minus part. So now we just have the plus, and then like I said before, we're going to take this, integrate it from negative r to r, and then double it, right? So we will integrate this from x equals negative r to x equals r, and then so we're integrating square root of r squared minus x squared dx, and then we are doubling it. So this is the main integral that we're going to use to find the area of a circle. Okay, so the way we're going to evaluate this integral, since we have a square root of something squared minus x squared, this kind of signifies to us that we're using a trigonometric substitution. More specifically, we're using the trigonometric substitution that says x equals r sine theta. If you're not familiar with trigonometric substitution, you might want to go look at that. So anyways, if we do the substitution, we will get 2 times the integral from x equals negative r to x equals r. We will have the square root of r squared minus, so if I substitute r sine theta, I will get r squared times sine squared theta. Okay, and then now notice I have a dx here. I want to have a d theta because I'm integrating with respect to theta, right? So how do I switch the dx into some kind of d theta? Well, the way we're going to do that is we're going to take this equation here, x is equal to r sine theta, and we're going to take the derivative of it with respect to theta. So if I do that, I will get dx over d theta equals r cosine theta, because r is a constant. So if I solve this for dx, I'll get dx is r cosine theta d theta. So whenever I have a dx, I can replace it with r cosine theta d theta. That's exactly what I'm going to do here. I will take the dx and I'll replace it with r cosine theta d theta, like that. Okay, so now I can simplify this a bit more. I can take the r squared, factor it out, and I can even pull it out of the square root because it's an r squared. So if I do that, I will get 2 times the integral from x equals negative r to x equals r of r times the square root of 1 minus sine squared theta, and then I'll have an r cosine theta d theta. Notice, by the way, that we have x equals something in our bounds, and then our actual integral is with respect to theta. So we're going to deal with that issue when we come to it, but for now, let's just keep on going. So the reason we did the substitution in the first place, that x is equal to r sine theta, is because this is actually equal to the 1 minus sine squared theta part. That's equal to cosine squared theta. That's one of the trigonometric identities. And then if we take the square root of cosine squared theta, we'll get cosine theta. So this is really equal to, from x equals negative r to x equals r, this is equal to r times cosine theta times r cosine theta d theta. Okay, so what I can do now is I can take this r and this r, and I can kind of pull them out of the integral because they are constants. So I'll get 2r squared, and the integral from from x equals negative r to x equals r. I'm really being specific in writing x equals, so I remember that these are not the bounds for theta, they're the bounds for r, for x. So I have the r squared, and then I have a cosine and a cosine, so that'll give me a cosine squared theta d theta. And then this cosine squared theta, the way we integrate it is not popping out immediately. The way we're going to do it is we're going to use another trigonometric identity. The identity says that cosine squared theta is equal to 1 plus cosine of 2 theta over 2, like that. Okay, so what I can do is I can take this 1 plus cosine 2 theta over 2, and I can replace it for the cosine squared theta in here, in the integral. So I will get 2r squared times the integral from negative r, I keep forgetting the x's, x equals negative r to x equals r, and instead of the cosine squared theta, I will put this stuff here. So I'll put 1 plus cosine of 2 theta over 2 d theta. Okay, and notice that this 2 and this 2 will cancel out. Okay, so now I'm just left with r squared times the integral from x equals negative r to x equals r of 1 plus cosine of 2 theta d theta. Okay, so this is something that we can integrate very easily. Okay, so we'll do this and we'll get r squared times theta plus sine of 2 theta over 2, and this is going from x equals negative r to x equals r. Okay, so again, there's a problem here. We can't simply substitute in r and negative r because this is with x and this is with theta. So we're going to find a way to turn these x's back into thetas. And for that, we're going to draw a quick triangle like so. Okay, so this is our angle theta. We know from up here that x is equal to r sine theta, right? So if x is equal to r sine theta, then sine theta equals x over r. And then I can say, all right, x over r is going to be sine of theta because sine is opposite over hypotenuse, right? So I can say that I want to express everything here in terms of x, right? So I can say, all right, if x is equal to r sine theta, then I can say theta is equal to, looking at this triangle we drew, I can say theta is equal to the inverse sine of x over r, or the arc sine. Okay, and then if I want to refer to sine of 2 theta, that's going to be kind of hard. So I'm going to use another trigonometric identity here, and I can replace the 2 theta with the sine of 2 theta with 2 sine theta cosine theta. So I will get r squared theta plus yada 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 2 sine theta cosine theta over 2, like that, going from x equals negative r to x equals r. So the 2's will cancel out here, and then I have the sine theta and the cosine theta. I can easily find expressions for these in terms of x. So we already know that sine of theta is equal to x over r, and the question is now, what is cosine of theta? So I have expressions for theta, and I have expressions for sine of theta, but I need an expression now for cosine of theta, right? The way we do that is by using this triangle. So according to the Pythagorean theorem, the squares of the sums of the two legs is equal to the square of the hypotenuse, right? A squared plus b squared equals c squared. So I can kind of use that, and I can use the theorem in reverse to solve for the length of this leg. And that'll give me that this leg is equal to the square root of the hypotenuse squared minus x squared. That's this leg. So if I wanted to find what is cosine of theta? Well, that's going to be the adjacent over the hypotenuse. So cosine of theta is the adjacent, which is square root of r squared minus x squared, over the hypotenuse, which is r. Okay, so now I have my expressions in terms of x for sine theta, theta, and cosine theta. I can substitute that into my integral now, or sorry, into my expression. It's not an integral anymore, is it? So r squared times theta is the inverse sine of x over r, okay, plus sine of theta cosine theta. So sine theta is x over r, and then cosine theta is square root r squared minus x squared over r. Okay, so this is my expression now in terms of just x's and r's, as you can see, and x is the only variable here because, again, remember r is a constant. And this is going from x equals negative r to x equals positive r. So this is pretty much going to be our ticket to the answer. I can now substitute in x equals r and x equals negative r into here, okay? So if I do this, I will get r squared times the inverse sine of, if I plug in x equals r, I'll get r over r, which is 1. Plus, if I plug in r into here, I'll get r over r, which is again 1. And then that'll be the square root of r squared minus, if I plug in x equals r, I'll get r squared minus r squared over r, right? And then if I subtract the x equals negative r part, I'll be subtracting the inverse sine of, so if I plug in negative r for x, I'll get negative r over r, which is negative 1. And then I will be subtracting, because it's negative, x over r is going to be negative 1, right? Because if I plug in negative r, I'll get negative r over r, which is negative 1, like that. And then square root of r squared minus, if I plug in negative r into here, I'll still get a positive r squared, because when you square it, negative don't matter, right? So over r, and this, and believe it or not, this is going to be actually equal to pi r squared. So we'll see how that happens, right? So notice right away that the r squared minus r squared is 0. So this whole thing is 0. So I can just take the entire thing and just draw an x through it, or whatever that's called. I don't know what that's called. Same thing here. We can draw a line and a circle through it. That's what I'll say. So simplifying this is r squared times the inverse sine of 1, and then minus the inverse sine of negative 1. Okay, so knowing your inverse sines, we know that the inverse sine of negative 1 is positive pi over 2. Or no, backwards. That's the other way around. The inverse sine of positive 1, is positive pi over 2. And then the inverse sine of negative 1 is negative pi over 2. Right, so if I can substitute that into my expression here, so this is pi over 2 minus, and then this is negative pi over 2, negative pi over 2, and then look at that. If we add pi over 2, so the two negatives make a positive, this is r squared times pi over 2 plus pi over 2 is pi, which gets us pi r squared. And we are done. That's pretty cool.